substances have a wide range in pH. And on this scale, I've written out a few substances that you probably use every single day, maybe some more than others, and then some you've probably never ever encountered before. Ammonia right here is a household cleaning product, and if you use ammonia at home, or any ammonia you have in your house, it's probably around a pH of 12. If you drink coffee every day, you know that you're drinking a substance that has a pH around 5. So coffee is mildly acidic. Right above coffee at a pH of 7 is neutral, and this is water at roughly room temperature, 25 degrees Celsius. Water will give you a nice pH of 7. Any pop you drink has a pH of 2, maybe just a little bit above 2, but I'm just rounding everything to whole numbers here. Okay, and then at pHs of 0 and 14, I have written out 1 molar hydrochloric acid and 1 molar sodium hydroxide, respectively. And what we're going to do in this video is look at the hydronium concentrations of these different substances based off of their pH. And I'm going to show you how the concentration of hydronium changes with individual changes in pH. All right, so let's start down here with a pH of 0 for 1 molar hydrochloric acid. First off, why does this make sense? Well, a pH of 0, if you remember pH is really a logarithm. It's the negative logarithm for base 10 when applied to 10 gives you the concentration. So the question then is, what number does X represent that when applied to a base of 10 gives me my concentration of 1? And we said that X, representing the pH, is the negative logarithm to base 10 that would give me 1. And if you do this in your calculator, or maybe you can even do it in your head, there's a certain exponent that when applied to a base always gives us 1. And that exponent is, well, it's going to be 0. So X has to be 0, and since there's no such thing as negative 0 or positive 0, we just write 0. So what this means here with our hydrochloric acid concentration is we could write it like, you could write it as 1.0 times 10 to the 0 moles per liter. All right, so that's the concentration of hydronium ions in 1 molar hydrochloric acid. And notice what we did here. If we want to actually write out a concentration of something, I did 10 to that pH, and because 0 is negative, I didn't have to write the negative sign in. But otherwise, if you want to find the concentration from a pH, all we do is we write the hydronium ion concentration equals 10 to the negative of that pH value. So if we want to go in reverse, we take hydronium ion equals 10 to the negative pH. So what's the concentration of POP? So it has a pH of 2, so I would do 10 to the negative 2. So that would give me a concentration of 1.0 times 10 to the negative 2 moles per liter. And if I write it out as a decimal number, that would be 0.01 moles per liter. Let's do one more for coffee here just to compare. Coffee would be written as 10 to the minus 5, which would be written out as 1.0 times 10 to the minus 5 moles per liter. And it written as a decimal, 1, 2, 3, 4, 5. It looks like that. So let's just make sure. 1, 2, 3, 4, 5. Yeah, that's right. So how do these concentrations compare to each other? So if you look at POP has a pH of 2, and it gives us a hydronium concentration of 0.01. And then if we look at coffee, its hydronium concentration is 10 to the minus 5, which is 0.00001. So how do these two numbers compare with one another? Well, to get from a pH of a concentration of 0.01 to 0.00001, we'd have to divide by a power of 10. In fact, we'd have to divide by 10 to the 3, which is 1,000. If I wanted to go the opposite direction, if I wanted to go from something that has a pH of 5 to a pH of 2, its hydronium concentration would have to multiply by 10 to the 3. So, what does this all mean? Well, what it means is that for every 1.0 increase in pH, so if my pH is increasing from 1 to 2, my hydronium concentration will decrease by 10. So it's like I divide by 10. So if I want to go from a pH of 1 to 2, the hydronium concentration goes from 10 to the minus 1 to 10 to the minus 2. And 10 to the minus 1 is 0.1. 10 to the minus 2 is 0.01. So it's like I divide by 10. So a substance that has a pH of 2 has 10 times less hydronium ions than a substance with a pH of 1. Let's look at another example. Let's say let's go 2 to 5. Well, this means I'm going to go from a hydronium concentration of 10 to the minus 2 to a hydronium concentration of 10 to the minus 5. And it's just like what I was doing here. In order to get that, I have to divide by 10 to the 3. And 10 to the 3 is actually 1,000. So what this means is that coffee with a pH of 5 has a hydronium concentration that is 1,000 times lower than POP with a pH of 2. Okay? So it's important to kind of know here that because the pH scale is a logarithmic scale, it's actually showing us this exponent. It's showing us the exponent. So what it means is every 1.0 increase in pH represents a 10 times, how do I write this? 10 times, let's just do 10 times decrease in the hydronium concentration. And the inverse is true also. Every 1.0 decrease in pH represents a 10 times increase in the hydronium concentration. Okay, so what this means is, something with a pH of 7 is 10 times more, acidic than something with a pH of 8. We could even look at these ones, like 1 mole per liter sodium hydroxide. What is its hydronium concentration? Well, its hydronium concentration would be 10 to the negative 14. It's really, really tiny. So 1 molar hydrochloric acid has 10 to the 14 times more hydronium ions than 1 molar sodium hydroxide. So it's quite a big range there. All right, so to summarize, if you haven't kind of gotten it yet, because this is a logarithmic scale and it's representing exponents, you need to view each change of 1 between exponents here as a 10-fold increase or decrease in the hydronium concentration. All right, and the second thing we covered was how to find hydronium concentration from the pH. In the next videos that follow, I'm going to do some examples of how to calculate pH for substances that don't necessarily have nice clean-cut concentrations like this. So stay tuned for that.